So now what we did in the last time, that our reaction rate, which is the W, we mentioned equal to 2 pi h bar, and then you have a wave function. This is, sorry, final state, and this is interaction part, and then you have an initial state and the square, and then you have a dn, or sorry, d rho by de, or like that, df, that we calculated, and this is the function of energy, and this is equal to nothing but our the cross section, the sigma va by v, where va is my velocity of my incoming particle or the incident particle, and the sigma is the probability of reaction, or the rate of reaction, probability of reaction, and that V, capital V, what I mentioned here, this is the volume, or the spatial volume occupied by the beam particle, and which we already know that one, because last day I mentioned that is, if I consider Na is the total number of or particle density, if it is a particle density, or a particle, oh, density, oh, this is writing is a little bit, this is a particle density, and then the V should be equal to Na is the total number of particle in the projectile divided by the particle density. So that is the V what I mentioned here. So now we showed you how to calculate this one and what is the value of this one, and only part we left with this, that is the your matrix element. Now we consider the precise case, that is the electron scattering case. So if we consider the electron scattering case, then obviously, and we consider the velocity is near the velocity of a light. So what we calculated this one, this value, this is the dn, d rho by d. If we remember, um, uh, then we can write whole stuff like this. This is the dnp, what is last time we calculated, and dn, and this is uh, the function of your momentum p, or p prime, equal to what we calculated is a 4 pi p prime square and d prime capital V divided by 2 pi h cut cube, that we calculated based on the phase space. So now if you insert all the value here, and if we consider, maybe you can just insert this one, that is a, uh, and we consider that the electron scattering, uh, my electron is here, and then it will be scattered off due to this target. We can say this is my target nucleus, and this is my projectile, which is basically the electron is my projectile. So, and because it is passing through this interaction zone, and because this interaction between the electron and the target is based on the electromagnetic because of the electromagnetic interaction, and you can see the, because of the very high velocity, it will cross this target within a very short time. So therefore I can consider uh, this scattering process is a stationary process, and then if I place my detector here, which can collect the information of my the electron, which I use for electron scattering, for this scattering experiment. And you know the detectors, each detector is having the finite solid angle, and if the solid angle is denoted by the d omega, and that is the angle subtended by this the area of your detector at the center of at this point. So that means this is the angle subtended by uh, this detector. If the distance is from here to here is r, so then I can, and the area of the surface area of the detector is a, then d omega is equal to nothing but dA by the r square. This is by the solid angle. So now if I consider the within the solid angle, the probability of cross section, so then I can consider the differential cross section, that is mean the d sigma. If I consider this one equal to d sigma, then the Vx Va by A equal to sorry, this one I just this is mm, 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 sorry, it's a again problem. Where is gone? Oh, it is already okay. Share.
What happened?
It is some problem with some problem, technical problem. For sure, it is not coming. I have to stop sharing. Uh,
Um,
share the screen again.
but
It's
nobody's
back.
sharing, so nobody's sharing, so you can share.
Yeah, now it's
Yeah,
okay.
it's back.
Back. Yeah, there's some. This program is actually Zoom. The problem with the Zoom and this program, this handshaking business is not. It's not done.
It's okay. It's okay. Please continue.
Okay, so now the d sigma is because I am considering only finite solid angle here, so therefore I can try to calculate what is the differential cross section, not the total cross section. When I talk about the sigma, sigma can be the total cross section. That means uh, the particle which will be scattered off through 4 pi 4 pi space. But here I am only because my detector has a finite solid angle, so therefore I am only concentrate about the small part of the cross section, that is called the differential cross section d sigma. So therefore the va by v is nothing but then the w, maybe I'll not write the w, and then it's equal to the same stuff will become here. This is the 2 pi by h cross, and this whole stuff will be there, and the psi f h interaction, then the psi I, then this is square, and this what we can write in terms of a this one. So that is a v. Um, maybe I can consider is a mod of this one, then it will be better for me. The p prime, um, p prime, and this is the square because this term is the square, and then we have a 4 pi term is be here, then the dp prime, this one, okay, and divided by your 2 pi h cube by by the de f de f, okay. This is a final state. Okay, so now this equal to, now if we consider the velocity va is approaching, the va is approaching the velocity of the light, so then I can consider the momentum, this is p prime, the final momentum, which is nearly equal to e by the e prime by the c. So then the de prime by de equal to 1 by c. So now I can rearrange this one, and this is the for the small solid angle part I have to include here, because I mentioned that I am only bothered about the this area, how many particles are coming. So I have to then multiply this one term, that is my solid angle. So this my the d omega term will appear here. So now you can see, now if you just rearrange this and consider this term, and put those information here, then I can get the d sigma by de, sorry, d omega, d sigma by d omega equal to d sigma by d omega, that is equal to, and just putting the all the value and rearrange. a little bit with the 4 pi, then is the 2 pi, and this is the your 8 pi, and then you can simplify all the stuff, and then you will get basically 4 uh, of 4, and this will be cancelled, 2 pi will be cancelled, and then rearrange all the stuff, then we can get directly v square e prime square e prime squared then 2 pi h, sorry, 2 pi square, not h I'll take out here, maybe I just a minute, I just here I can write this is, then it is a then it is a 2 pi square then h c square, this is square, this is the 4, sorry, this is the 4 will come, and then you have a your matrix element psi psi f h interaction and the psi I, and this is square. So this is the cross section, the differential cross section d sigma d omega, what you can calculate for the for the electron scattering case if you know this particular term or the matrix element. So now our next step is to calculate the matrix element. How to calculate the matrix element? So we'll go for a next one. How to calculate the matrix element? So how we'll calculate the matrix element? So just we consider only matrix element part, and uh, consider the case that for the matrix element part, what is I can write as a, I have to remove the keypad from here, otherwise it will give me problem. Yeah. What I'll do that I then we write down the matrix element. This matrix element we can maybe mm, yeah, matrix element. So that matrix element maybe we can specify by I like this. This is equal to my psi f h interaction and the psi initial. Okay, I'm not putting square right now. So this is my the matrix element, and which if you can write in the integration form also. This is if you write in the integration form, that is the psi f star, and this is the h interaction part, and then your psi initial, and then you have to perform this integration all over the space, that is d r. So this is your the matrix element. Now we have to find out what is the form of the wave function and what is the form of this interaction between these two states, because I mentioned this is the two state problem. This is the maybe the psi I, and this is for the psi final, and it will be interacting through this interaction. This is the H interaction. So now our case, this interaction is a simplify. It's very easy because this electromagnetic interaction is a well-known interaction for our case. Huh? So therefore, we can write this interaction, and also because the electrons, we can write this interaction as a Coulombic interaction, which is can be write as a the VR, which is my the Coulombic interaction. This is H interaction. Also, you can say this is nothing but my the Coulombic. If the charge of the nucleus, say for consider a nucleus which is like this. So this is my nucleus with a the density, charge density is a rho prime r, and you say this is my center of mass here, and the electron is coming from here. And after seeing the interaction, after seeing this nucleus, some nucleus is present here, so then it will be interact, and some type of the photon will be exchanged. We will because of this interaction. After this interaction, it will go back, go to other direction. Say, and this the if I consider the momentum of this particle is the pi, or I can say the wave vector, which is going to be represented by the ki, ki, and the charge of this one, because the electron, so the charge is e. And after seeing this nucleus, maybe it is at this distance from the center of mass is center of mass, say the r. So, and here you can say some arbitrary radius r prime. Hmm. So therefore and you try to calculate what is the interaction at from this point to this point. So that means the radius or the distance is say this distance, then it should be the r minus r prime or vice versa, because it's a mod I am taking. So after this, seeing this interaction, the if electron can be scattered elastically or inelastically, for time being we say the some type of scattering, and then the momentum will change from pi to ps, and corresponding momentum or the vector part we take, it can be written as kf, or the wave number, which is a uh, basically all are vector quantity. This is a wave number kf, and this is the ki, and this is the momentum pi and the ps. So then the sigma, if I consider, is a plane wave. For the very simple case is your the wave function which I consider for, the electron is having, or we can say the electron is associated some type of plane wave. Then we can write immediately the type of wave function, say the psi initial, I can write as a e to the power the minus k r, k initial, and this r is my the radius vector. So then if you want to normalize this one, so it is not a normalized wave function, but if you want to normalize, then you can normalize it by some vector, because you know the total volume is the v. So then I can have a extra term I can get is a 1 over root v, uh, can be used as a normalization. Again it is stopped, so I have to reshare again. Okay, hope it is back to you. So this is my wave function, now the incident wave function. And if you try to write the normalized wave function, then one extra term will be appear. This is 1 by root v, and this v is because of the total volume I am considered is a v. So therefore this can be the initial wave function, and after scattering, then my wave function should be that 1 by root v e to the power I k f r. So now if we can, if I can put it here, and also the what is the V interaction? V interaction is nothing but the Coulombic interaction, and if my the nucleus is having the charge is Z, and the charge is E, so therefore the nucleus charge then is a Z, and then the electron here, one electron, then it's a square, and then here some quantity to comes equal to 4 pi epsilon 0. You know that's quantity. And then you have the integration in the whole your nucleus. So I know the density, because the density is the rho is r prime, and your difference between r minus r prime, the dq, because the last day also we discussed how the interaction is look like, Coulombic interaction, not last day, few days ago. So this is by the Coulombic interaction. So now I just insert this v value and also the wave function value here. So then I can get my matrix element mi, sorry, mfi equal to, first I am just inserting this matrix element, so e to the power minus I k f minus I, because you have a the size star here, and dot r, because it's a vector quantity, so you have to basically write this is dot here and also dot here. This is the all a vector quantity, there is a dot product, and then you have a vr here, the vr, and then e to the power I k initial dot r. I, everything is a vector quantity, so I should also mention here, so dqr. Or you can write e to the power minus iq dot r, where the q is the difference between uh, I k f dot r. This is the q is nothing but the ki minus the kf. So this is my q dot r, then vr vr, then dqr. So this is the your the matrix element. So now you have to insert those value here. This insert the v value here, and what we'll get, that you can see from here. If we insert, so then just we remove the vr, maybe next page, or maybe here we can do just removing the vr from here. Uh, where is the view? Oh, nice. Draw. Mm, So if I remove from the VR here, and we insert this value here, so we can insert this value here to get, uh, so then you have a z is square, right? Because, and then divided by 4 pi epsilon 0, and then you have this quantity, this quantity, um, and you have another integration, because this another integration will come, so this is the another integration, then it is where rho r prime by r prime dq r prime dq r. So this is my then the interaction, this is a5. Now we can take a few assumption, or the few the condition we can impose, that if r, for simplicity I just try to say the r equal to r minus r prime. Okay, so if I say the r minus r prime, and we this is the condition, and and we can consider this one, the r is very large compared to the r prime, and then we can easily write dq r, because r prime will be very small. So dqr equal to dqr. Okay, so we can use this one for simplicity. Uh, just we can assume this condition. So then if we put this value here and segregate a little bit, so then this will be the z square by 4 pi is square. But you can take also the minus sign, because if you consider what is attractive potential, this is the, because it will be attraction. So you can put some minus sign here, but that is up to you. So whether you can put it or not. So anyway, so then this is the 4 pi epsilon 0, and then e to the power minus q dot r, and this quantity e to the power minus q dot small r prime rho r prime divided by capital R dqr r prime d q d3 r. So this I just rewrite just and condition because this is r prime, it will be here, and instead of a dr I am just writing the dqr, and this one already I assume this is equal to r minus r prime equal to r, so this is my the capital R, and this r because this r prime can be neglect that I mentioned this r for the large value of r, so I can consider r equal to small r for the for simplicity, so then it should be the q dot r. So this is the few assumption I am using, but you but if you want to do the proper way, the proper if you can without assuming this one, things will little bit more the mathematically more complicated. So I just try to avoid those complicated mathematics, and give you the some simply idea how to do the calculation in the if you use some of the very basic assumption. Okay. So now then I can rearrange this one and try to calculate my or I try to rearrange this thing again, and then the my uh, mfi. Oh, actually every time I have to write also this your the mod value here, so maybe I should not write the mod here. And so I should not write, yeah, I should not write the mod. Otherwise, every time I have to write the mod. I should not write the mod value here. So the my matrix element then equal to z is square 4 pi epsilon 0. So e to the power id dot r. Everything is a vector quantity. Please be remember. Somehow I am not writing sometime, but everything is a vector quantity. Yeah? So every time those are the vector. So when I just saying this one, it should be always you have to write always the arrow on top of every number. Huh? Those are the vector. So now this is the q dot r quantity, and then divided by r, and this is your dqr, and then other integration part. This is the two integration here. What you can see. Oh, I missed another integration. Yeah, there should be the two integration dqr. This integration I missed, so it is be like this. Uh, so or this integration part e to the power I q dot q dot r prime rho r prime dq r prime. So now we can see we have a two separate integration. One integration is solely depends on the r, and other integration is solely depends on the small r prime. And this quantity, this particular quantity, what you can see from here, if I put this equal to 1, if I say this is equal to 1, so then what will be it will be easy to solve this one. This is very easy, e to the power q dot r, and so then, so if I consider, if I consider the r prime is nearly 0. What do you mean by r prime nearly 0? That means your nucleus, because here what is the r prime? R prime is the distance from a point, distance of a point from the center of mass. Now, if I consider r prime is 0, this is nothing but a the point-like object. So therefore, if your nucleus is a point-like object, so then this quantity, this particular quantity, then is goes to 1, because r prime equal to 0. So this quantity e to the power k dot, yeah, this is the 1. So this is totally quantity goes to the 1. So, and this quantity is called the, it can be represented by the fq, Fq equal to e to the power I q dot r prime, all are vector quantity, rho r prime and dq r prime. So this quantity Fq is called the form factor. This is the form factor. Nuclear sometimes is called the nuclear form factor. This quantity is called the form factor. And you can see if r prime is 0, this quantity goes to 1. For r near to 0, then Fq r goes to 1. For the point like object, then whole thing will be modified. And this probability, then you can see that means this quantity, if you don't have a this the point like object or the spherical symmetric shape, so then this if you are, or you have a finite radius, then this quantity is important. So therefore, if you know this quantity, then you can also talk about the distribution, the nuclear distribution or the charge distribution inside the nucleus. So that's why this quantity is very much important. And if you take the Fourier transformation, we can see that you can easily calculate, because right now you are in the momentum space, because the q, you are the momentum difference between the two momentum. So therefore you are in the momentum space. So if you want to calculate the radius, then if you want, if you can take the Fourier transformation of this quantity, so then that will give you the radius of your the nucleus. So therefore the importance of this quantity you can understand now. So that this quantity, this a form factor, if you take the Fourier transform of this form factor, then you can get the the what is the radius of your the nucleus. Okay. So so therefore this quantity is very much important to understand the nuclear size or the nucleus nucleus radius. Now for simple case, when you consider the elastic scattering, so if you consider the elastic scattering, because we are just talking about the elastic scattering, or maybe I can just show uh, one information here, maybe where here, just see where it is. I note down. Yeah. So if you can see this, if this is the form factor, whatever talking about, if you have a form factor, different type form, if it is a constant like this is some constant value of the form factor. When you change in the x-axis the momentum, this is your momentum direction here, and if you change the momentum, that means during the scattering, if you try to do the angular distribution, that also can tells you the energy, tells you the change of momentum, or you can take the different energy, that's also give you the momentum, the change in the momentum. If you try to plot this one, so then, and this value, if it is the value of this f is coming a constant, then it should be the point like the distribution should be the point like, here you can the radius, and here the distribution, the what showing here. So this is the point like distribution. If it is a constant value, what you will get. So normally for the electron case, you can get a constant value. But if you have some type of distribution, this fq square has some type of distribution, some type of exponential uh, um, decaying type of thing, so then one can expect that a dipole type of contribution. And this is generally observed in the proton case. Uh, or if you go into the Gaussian type, then is the lithium, and so that. And if you some oscillation, you will get that may be due to the finite size of the nucleus. This is the some more or less experimentally observed shape, and then we try to based on this shape we can easily explain what type of uh, scattering, how the radius is varying with the how the radius is, uh, or you can calculate the radius of particular nucleus. Okay, so maybe you can see some. I don't know whether I have shown here. Oh, I missed that figure. It is not here. So, sorry, it is not here. Anyway, now come back to here. So now, if you consider the elastic scattering, form of the elastic scattering case, for electron scattering case where the ki equal to kf. I am not because every time those are the vector quantity, so it is equal to the k. If I consider this one, so then the q, I can write the k initial to k final, which is can be write as a k I square plus k k f square minus 2 ki kf cos theta. Okay, so then this quantity we can write this way, and then we can write this is nothing but your uh, 4 pi, because the k I and kf are same. And then if you do this one little bit juggling, so then this is the 4 k square sine square theta by 2. That you will get it here, huh? So this is also so now so now if we now try to calculate what is the value of the radius, then immediately you can calculate from here. So now, yes, I think few seconds or something like that. Okay, and also you can calculate this is fq, um, or you can rewrite this fq more better way. So I am not going to do this derivation, small derivation. You can put q dot r equal to sine your cos theta, and then this fq can be write as a little bit more much better form. This is a 4 pi rho r rho r square rho r square uh, dr sine qr by qr. So this is the form you can use, or you can use equal to 4 pi rho r, just using the Bessel function, the 0 qr r square dr. Okay, you can write in this form also, huh? So that you can do it easily, just putting the just little bit of a few step of mathematics you can do it, huh? So I am not doing. So then you can write in this fashion also. So now we can consider now this q square, or the momentum change of the momentum is very small. So that means that if you consider the q is goes to 0, or better you can say the q square is goes to 0, or q is goes to 0, you can say. That means there is a small change of momentum. So then I can, then I what you can see, this fq, this quantity, or maybe this quantity can be the sine qr can be expand in the power series. And if you expand this one in the power series, then it should be, then is a 4 pi. Okay, it should be the r prime, huh? So everywhere it should be the r prime. I missed this r prime here. So this is, those are the r prime, those are the r prime, those are the r prime. Okay, and this one is also the r prime. So this one is a 4 pi r prime square, then rho r prime. And then if you expand the sign, you know the sign expansion, this is the a, if it's the sin x expansion, the sin x expansion is your x minus x cube by 3 factorial, then plus x to the power 5 by 5 factorial, and so on, minus so on. It is the series what you will get. So I just, when you consider the small momentum, change of small momentum, so then I can expand this quantity. So if you expand this quantity and rearrange a little bit, and then you can get the 1 minus 1 by 6 q square r prime square, the plus dot 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 dot, the dq dr prime. So now you can see if you neglect all the quantity, then only quantity will get. This can give you the radius of the nucleus. So then we can say this is the radius, which is the a square. We can rename this one a square equal to then your 4 pi r prime square rho r prime dr prime, and this is called the root mean square radius or the RMS radius. This is called the RMS, the radius of a charge distribution. So this is the RMS radius of your the charge distribution. So how this charge distribution is look like? Maybe I try to see whether I draw something, or maybe I have to go to the next page. So the charge distribution generally look like, if we plot it like this, this is the rho r by r, then the charge distribution from the electron scattering you can get like this type of distribution. You have some flat edge here, the saturated, and then after that it is smoothly going down. So some of the experimental result I can show you here. Oh, um, sorry, I don't know whether I have it here. So look like some, no, 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 no. Where it is gone? Uh, no, it's also not here. This is 11, 12. Yeah, yeah. This is the charge distribution from the electron scattering experiment. What you can see, this is for the electron is hitting on your the helium, then you can get the distribution like this. And if you go for the heavier uh, elements like a calcium to lead, what is for calcium, nickel, samarium. So we can see the how the distribution is look like. This is the charge distribution. How the charge distribution is look like. But the cross section you know how to calculate. So now if you can rewrite the cross section, d sigma by d omega, this is you can get from the experiment, and then you would compare with the what you have calculated uh, from your theory. This is the d sigma d omega what you have calculated, and then you have a f q. This is the square. Okay. So what you can see, this is you have calculated, and this is generally called the Mott cross section. What you generally calculate, because the till now what I showed the cross section, this cross section, uh, the cross section what I mentioned here through this where is gone, maybe here, yeah. So like here, yeah, this cross section what I mentioned here, from here you can calculate, here you can see that we have not included the spin contribution, because an electron is having the spin and nucleus also is having some spin, so therefore you have to include the spin contribution. So the cross section what you will get from here, the for pure spherical system, you will get a Rutherford cross section. So now you have to include the cross section. This is a d sigma. What you will get from here, it is a Rutherford cross section, or the classical cross section, Rutherford cross section. But when you include the spin effect on this cross section, then we can define this cross section as d sigma by d omega is a Mott cross section, MOTT, equal to extra quantity. Generally you have to add because of the spin part of your wave function, and this is your Rutherford cross section, and then you have to multiply by one quantity, 1 minus beta square the sine square theta by 2. Theta is the angle between your the incident particle and the scattered particle, and this is, and the beta is equal to the incident velocity by the c. So this is the then the small scattering cross section. So now, if you compare your the scattering cross section with a Mott scattering cross section, so then you can get 12, uh, 13. What is called 12, 12. This is yeah. So now, if you now you'll get the mod, this is the mod scattering cross section. You will calculate the way I mentioned, and then you compare with the experimental cross section. Then you will get the quantity f q squared or the form factor, and the shape of the form factor then tells you what type of nucleus it is, or how what is uh, the size of the nucleus, that you can get it. So some of the result you can see here uh, how the distribution is look like for the proton case. If you are considering is the only the proton distribution and try to use the electron scattering experiment, and then you can see this is from the two type of distribution. This one is the charge distribution, what is mentioned by red color here, and then you can get the matter distribution, which is quite different from the your charge distribution inside, because you can see the from here to here the radius is of the order of 1 Fermi, and then it is a it's look like you have some saturation here, and after that it is continuously falling, and this is, you can say, the some type of the softness of the nucleus, and or the surface is much softer. So therefore you, but here the hard portion is here, up to maybe you have a hard portion, and after that nucleus is much softer. So so therefore you can have a two quantity, uh, uh, one is for the charge distribution and other is for the matter distribution. So now if you use the two different type of uh, the, this for the electron scattering case, you can only probe this distribution, which is the charge distribution. In the matter part of the distribution, obviously you cannot probe. So therefore you need to have a different type of probe, like a proton probe or neutron probe, that can be useful to find out the both the distribution, charge distribution, as well as the matter distribution. So therefore the electron scattering experiment, I will only get this the charge distribution, where here you can see the green color is the matter distribution, and the red color you have a charge distribution, and the white, this is means the uncertainty of your the measurement. So therefore you can see that for the very low radius, you have a larger uncertainty, and then if you go in the surface of your nucleus, then the uncertainty is much smaller. So therefore, also electron scattering or any type of scattering, it will be very difficult to give you the information, uh, detailed information of the nuclear potential, because what you can see the density actually, or how the inside the density, that will be very difficult to tell, or the structure of the particle. It will be very difficult to tell from your electron scattering. It will give you some type of gross feature of your nucleus. Okay. So with that, I think we can stop for the neutron electron scattering case. Maybe the next day we can try to do nuclear reaction, or maybe go to the shell model. Depends upon the what Professor Gautam Ganguly will do. So accordingly we decide and we'll let you know. Okay. So now we can answer few questions. If okay, I'll see there is any question. Oh,
When you have no questions, then either your lecture was too clear
or it's not clear.
or nothing was clear.
Nothing else clear. Yes.
There is a question from some. There's a question from somebody, Priyoda,
Sir,
in the
could you
chat box.
explain density distribution plot a bit?
What?
Sir, could you explain density distribution plot a bit? It's written in the QA box. No, chat box. Chat box.
That a density distribution. So what you can see here from we have a two type of density in the nucleus. One is a your charge density, and other is your, if I plot like a radius along the x-axis and the density along the y-axis, because your nucleus is having a finite size. So therefore, I expect some densities. If there is a no softness, then I should see some type of sharp boundary here. So it is a sharp fall. But what you can see from the experiment, the density distribution. If I consider, say that I have a spherical nucleus, and the boundary is very well defined boundary. So and everything is a solid here, solid sphere. So there is no softness, nothing is there, solid sphere. So then one can expect a density distribution is look like this, is a sudden fall of a density from very high value to very low value. But what we can see from the electron scattering, the density distribution is not look like this. You have a some type of the softness here, and this softness we generally call the diffuseness parameter, or the diffuseness of the nucleus. And this exponential fall, we say, uh, or the meaning of this exponential fall, we can say like this, that the nucleus is very hard inside, and then you have a some type of the soft cover. Again it's gone. Yeah, it's back again. Yeah, so now you have a soft cover, and the top of that you have a some type of sorry, you have a solid nucleus, and then after the top of this you have a some type of soft materials are there. So therefore you will get some type of the this tail behavior which is observed during the electron scattering experiment. And this is mainly because, as I mentioned, the electron is a negative charge particle, and the nucleus, inside the nucleus, you have a lot of protons. So therefore, electrons can only probe the proton distribution inside a nucleus. It cannot it cannot probe the neutron which is present inside the nucleus. And also this the this from this density distribution, what you can see is the gross features of the nucleus. It cannot tell the internal structure of a particular nucleus. It can say only the gross structure. This density distribution can only give you idea about the gross structure of a particular nucleus, not the detailed structure of a nucleus. Okay, hopefully it's okay. This is the answer. Okay, if there is a no answer, no question, is there any
Sir, there are questions in the question and answer box.
question?
Two questions are there. Yes, sir.
Why the charge density of a neutron is the 6 times the charge density of the proton? No, this is not the true for the all time. This depends on the nucleus. It is vary from the nucleus to nucleus, which nucleus you are considering. So nuclear, in case of a say say the oxygen nucleus, where the number of neutron and number of proton are exactly same. That is the 8 number of neutron and 8 number of proton. So in that case, this difference is very small. So this is not valid for all the nuclei. So some nuclei where you have a larger neutron number. So in that case, your density will be the more. Okay. Sir, please explain which parameter is related to the spin in the Mott scattering. No, I'm not actually explain how the spin included in your calculation. I just simply show, because it is bit involved calculation. So therefore, I just mentioned is if you what you can see from uh, this matrix element calculation there. If you where is gone in your matrix element calculation, we consider, well, consider this wave function and this wave function. We are considering is coming from the particle, which is an electron, though it is having the spin, but we omit that's the spin part of the contribution in your wave function. But this spin part, if you include in your wave function, then you get a extra term which is like this in your calculation. In your not calculation, in your expression for this scattering cross section, this extra term you will get, and therefore then your cross section has to be modified, and this modified cross section is called the Morse cross section, which is nothing but the cross section which is Rutherford when you are not considering the precise spin information in your wave function. So, but now if you include that spin information, then this extra term will come, and this should be multiplied by your the classical cross section or the cross section which you have calculated by considering without spin effect. Okay. The DN Gupta, what device I am using to write? This is the this pen tab I am using to write this on the screen. This is the suggested by the Saurabh, in fact. Okay, so if there is no other question, so then I can stop and move to the
Last question. Are these experiments to calculate form factor curve or is it just theoretical?
as I
Can you?
mentioned here. So to get the size of
अरे
the
मैंने ध्यान
radius,
नहीं किया ना मैं अरे मैं क्वेश्चन
Okay, Poonam, your mic is on.
so so how to extract the radius of the nucleus. So, and I mentioned the form factor contain the information about the radius of a particular nucleus, and then to extract this form factor value, you have to compare with your experimental data with your theoretically calculated Morse Mott cross section, and this the ratio between these two will give you the idea about the FQ that I already show here. Some of the here I can say this is the FQ was plotted, and if you get a constant behavior, then I can see the point like type of structure. If you say is a some type of exponential behavior, then it's a dipole type of structure. And then Gaussian shape, different type shape you can extract from this, and from there you can calculate the size of the nucleus. Here you can see this is your the moment your density distribution, and density distribution can shown here, and this is your the if you plot it in the x-axis is r and the y-axis is the density, and then from there you can see this is your the radius of the nucleus, which is called the RB, or the half radius, generally called the half radius of the nucleus, which is the point here. And this from the 9 from the 10% to 90%, 10% of the from here to 90% of this is called the diffuseness of a particular nucleus, or it's called the diffuseness parameter. And other is this RB is your the radius of a particular nucleus. And obviously this distance can be called the strength of this particular distribution as for the nuclear phase is concerned. Okay. Okay, any question? I don't think. Okay, this is clear. Okay, then I'll back. I just. Oh, I have not shared, no. So,
Yes, Professor Mandal.
are this experiment
Hey.
calculate? Hi.
Sorry. I thought you.
I mean, are you answering still a question?
I don't know, because I can stop here, so I cannot see because my sharing is stopped most to look
No,
like.
I read the question. Are there experiments to calculate form factor curve or is it just theoretical? This is the question which that was last.
So then I answered, no, this one that
Okay, and so
need
why
answer.
charged? Maybe you
Yes.
can stop sharing and have a look at the Q&A box.
Okay. Yeah. Where is the Q&A box?
Sir, one more question is there in the Q&A box from Harsh as well.
Sir,
That's what I
because
read. That's what I read.
no,
No, no, ma'am, another one from Harsh.
sir, because the electron turns out to have some structure and hence the form factor must come out not equal to the point charge. Is no. This what I am saying. The nucleus, because I am trying to extract the form factor for nucleonic distribution or nucleus a particular distribution. Now if you consider nucleus is a point charge, then I will get a the straight line that I mentioned. It's not that the electron is having a structure or something like that. It is a only the nucleus is having a particular structure and the shape. That's why I should not get a point. I should not consider is a nucleus as a point charge, because a nucleus is having a definite size and shape. That is it. Okay, so if it is fine, then I can stop here and hand over to
Yeah.
Kesh for that
Yes.
one.
Our next speaker
अब
is already
Huh?
here.
अब तुम्हारे हवाले वतन साथी हूँ.
Yeah, that's
Yes. So now you have stopped
Punita,
sharing.
Punita,
Yes.
it's okay. You can say that Mandal gave a very good talk. You don't have to. We won't say anything. Okay.
So let me thank the speaker for this enlightening talk. You see, when the physics starts, then all other senses stop, then all you can
Aha.
remember is only physics. then and then at least one sentence in every lecture will make you think, did you remember this always, or is it that you have come to know it now? So you get lost into that, arena. So
Hmm.
I really thank Professor Mandal for patiently explaining scattering to our attendees, and we're looking forward to your last session where you would discuss questions and numericals based on this portion very soon.
Samit,
yeah, yeah.
Samit, she's just making sure that you don't give another one. She said it's the last lecture, next
Last
one.
lecture. Yeah.
No.
I'll be happy.
At least one more lecture where at least, you see, then one more lecture with at least the numericals should be covered. But yeah, I mean, it looks like we should have 2 weeks for one subject, and still it's not enough. I planned 1 week, and it's really falling short, and that's what I can realize. But I think more than that, we just cannot manage. So thank you
Hmm.
again. And now we have our second speaker with us, Professor Sheshadri. And
Don't go over introduction again, please.
oh,
That's
no,
that's a boring actually,
this,
quite boring.
you see, for the new persons, it's not
Okay,
boring.
okay, okay.
You
Oh,
see, for
fine.
the new persons, it's not boring. For the
Okay.
person who has joined several times, okay. So I will make it short. So Professor
Okay, fine.
Sheshadri is an extremely considerate person.
Oh
He's
my God.
affectionate towards his students, and he's considerate enough to accept all requests on whatever we can't understand out of classical mechanics. I have heard that he explains small oscillations wonderfully well, and
Ah,
there are other things which we have made a list of, which we are going to request him to explain in the next class whenever he takes it. And his interest in cosmology and related fields is well known. However, he is famous for the most energetic and the most enthusiastic and the contagious enthusiasm teacher in
बोलो बोलो
Delhi
बोलो बोलो
University.
बोलो सुन रहा हूँ मैं बोलो बोलो.
I personally, I must confess, every time I've gone to Professor Sheshadri to speak even one sentence, I come back with more enthusiasm and inspiration, and it looks like I'm charged again. So he looks like some, eternal charger to charge people around, or
Hey,
maybe
don't praise me so
frequency
much
of.
here. I may start believing it. Okay.
So I'm thankful to him, and I welcome you to deliver your talk. And now, since you cannot share slides, so I request my co-panelists to share the slides that you have given us already.
Yeah.
So Dr. Parul, are you able to do it, or should I do it? So Mansi, Dr. Mansi is, yeah, here. Now you
Mansi
have,
is there. Okay. Hi, Mansi. Okay.
so now a little bit larger.
No, it's okay.
No, it's a bit small. You have gray portion. So try to enlarge it, please.
Okay.
Change the view. Oh, no, it's double page, no single page. No, you have to increase the, you have to
Maybe
increase the
fit to
size.
width. Fit to width. There is on top fit to width.
Yes. Yes.
Okay.
Now you have to be careful because he'll ask you to slide up and down several times.
Yes, yes, yes,
We'll
yes.
make sure
Actually,
that you revise
sir.
space trajectory.
yes, yes. Okay. Hi, everybody. Good evening.
Good
Uh,
evening, sir.
good evening.
Sir,
Good
today
evening.
also, yeah. Sir, today also you are not able to share the whiteboard.
Yeah, I mean, something very strange because day before yesterday I could share whiteboard. Today I can't share it.
Sir, maybe you have also got a message from Zoom because Zoom is updating from last 2-3 days, and I
Oh,
have got a message from Zoom. There are some features added to the Zoom. Maybe that is the
here,
problem.
no, no,
So
here it is subtracted
you
from mine.
no, sir. What I'm saying ki you
Huh.
want you right now you want to write on the whiteboard.
Yes. I mean, if I can.
Uh, Sir, I can suggest an alternative to you.
Uh,
Kindly go to some URL which I am suggesting you. It will behave as a whiteboard, and it is having inbuilt pencil and everything. And if you have your writing pen or pencil, then you can
uh,
go ahead with that also.
okay, I will do
So,
one thing. Let
yes,
me,
sir.
because it will take more time. Let me just go over this one. We will try it later.
Okay, sir. No problems. No
Yeah.
problems.
Yeah.
Okay. Yeah. Thank you.
Okay. Hi. So let me start by just giving a brief recapitulation of phase space trajectory, which I discussed yesterday. So what I had discussed yesterday was from the Hamiltonian equations of motion, I can write P dot by Q dot, which is dP by dQ, and that is a function of H, that is a function of P and Q. Now, the first feature which I mentioned was it is a first order differential equation. And the another feature is that it has no time information. That is, as I gave an example of a truck going through a desert and leaving a path, I know at what x coordinate, at a given x coordinate, what is the y coordinate, but I do not know from this path at what time this truck reached that point. Similarly, in the case of a phase space trajectory, I know that at a given position, what was the momentum of the particle, but I do not know the time when that position and momentum was attained. Okay, further down. Okay, and since it's a second order equation, a single initial condition uniquely specifies the evolution of the phase space trajectory. And because of this reason, the phase space trajectory of a particle cannot intersect itself. Because if it intersects itself, then from the point of intersection, there are two lines in the phase space trajectory going. But as we know, since it's a first order equation, once I have given a certain momentum at a certain position that is identified a point in phase space, only one line, only one solution can emanate from there. So the phase space trajectories of a particle cannot intersect themselves. Okay, next. And yesterday I gave some examples of phase space trajectories. So I will be building on it more. So I'll recapitulate this also. As I said, for a simple harmonic oscillator, we have this Lagrangian half m q dot square minus half k x square. And the corresponding Hamiltonian I write as h equal to p square by 2m plus half k q square. And then I can write the P dot and Q dot from the Hamiltonian equations of motion. I can calculate dP by dQ, which comes out to be this one. Solve this first order equation, and there is a constant of integration, which we identify as proportional to energy. Let's go down a bit. And so if I take initial conditions as P naught and Q naught, I get my energy as P naught square by 2 plus Km Q naught square, which is equal to M into energy. And so this is the equation of the phase space trajectory of the simple harmonic oscillator. And from the structure of this, we see that, okay, I forgot to correct it. I mean, this should be, as I told yesterday, it should be 2E by K in the graph. Go up, go up, go up. Yeah. No. Sorry, not up. I mean, go down. Sorry. This is what Punita was warning you. Okay, that I give confusing directions. Okay. So, so we see that the phase space trajectory of the simple harmonic oscillator is an ellipse. Now, as I said, the direction, the arrow, there is an arrow I have put, and the arrow is because this will always traverse it in the clockwise direction, because once I have the particle is in the positive maximum limit of Q, then it can only move towards zero. So it means that the momentum is negative. So it has to, if we start from the point which is marked there as the Q intercept, from there it can only go down and then traverse the whole path in a clockwise direction. Okay, and I also mentioned that the phase space trajectory has got an important implication for quantum mechanics. That is, the Bohr's correspondence principle basically says that if I go from one energy to another, the size of the ellipse will change, and the size of the ellipse can change only as the integral of P dq is n h cross. And so you have energy quantization. So this was the first, this was the initial way in which quantum mechanics was proposed as some kind of a thing which was built on the classical mechanics framework. Yeah, further, yeah, next. And then I gave another example, which is of a particle which is freely falling from a height h in a constant uniform gravitational field. And in this case, I had assumed that it bounces from a rigid floor, and the collision with the floor is elastic. And then the question was, what is the phase space diagram? So once again, we had the Lagrangian, we had the Hamiltonian, and we wrote the phase space trajectory as p square by 2m plus mgy equal to energy. And this is a parabola, as I have shown. And yesterday we had a lot of discussion about how it jumps from, it has a discontinuous jump. And as I mentioned, the discontinuous jump is because of our ideal assumption of the rigidity of the floor and the rigidity of the particle. If the floor or the particle could deform, then this will not be a discontinuous jump. And this is one example which I will take today. Okay, go down. Yeah, next. Okay, so now I will go over to another example. Okay, where the trajectories in phase space are not that simple. Okay, and the problem which I consider is that of a space path of a pendulum.
Excuse me, sir.
Yes.
Excuse me, sir.
Yes.
Sir, there is some background noise.
Is it that of an ambulance?
Yes, sir. Something
That's
like
because
that.
the ambulance is going near the main road. Okay.
Okay, sir. Okay. Fine, sir.
Yeah. Actually, there are a few hospitals about 2 kilometers down the road, so ambulances keep going. Oh, is it better
Okay,
now?
sir. Yes, sir. Quite better.
Okay. Fine. So, I mean, I will be discussing the phase space trajectory of a pendulum. Now, immediately when I say pendulum, people will ask, how is it different from this simple harmonic oscillator, which I had discussed? And the answer is, a pendulum is a simple harmonic oscillator only for small oscillations. And I will actually discuss the nature of the phase space trajectory of a pendulum, not necessarily for small oscillation, but also for any arbitrary oscillation, and discuss its phase space structure. Okay. So now I have this pendulum. I have a pendulum of length L, and there is this mass M, the mass of the bob. And at any time during its dynamics, the angle made by the suspension of the pendulum with the vertical, I call by the angle theta. So now let us set up the Lagrangian. I choose the zero of the potential as at the point of equilibrium. That is when the mass is straight down. Okay, no, I thought some question was there. Okay. Oh, there are just good evenings. Okay, good evenings. Okay. So now, okay. So at the point of equilibrium, if suppose the energy is taken as zero, then yeah. And so so there I take y as zero, and the potential at any point is given by mg into y, because as the pendulum oscillates, the bob of the pendulum increases in height. And so I can, okay, I should have marked it here. So if I take the projection of this length onto the vertical, it will be L cos theta, and the equilibrium position will be L. And so the amount by which the pendulum has raised itself is L into 1 minus cos theta. So this is equal to Y for the pendulum at this angle theta. And so the potential is mg into L into 1 minus cos theta. Now the kinetic energy is half m, and the arc length is L into theta. So the velocity is L theta dot. So velocity is L square theta dot square. And so you have half mass into velocity square, which is L square theta dot square. There is a different way also you can look at it. I can look at it from rotational coordinate system. M into L square is the moment of inertia for this system about the point of suspension, and theta dot is the angular velocity. So kinetic energy can also be looked at as half into moment of inertia into omega square, omega being theta dot. And so if I write the Lagrangian, I will get half m L square theta dot square. And Lagrangian has minus of potential. So I put that minus the potential which I have written, mgl 1 minus cos theta. And then I substitute this in the Lagrangian equation of motion, and I get ml square theta double dot equal to minus mgl sine theta. M and m will cancel. L and L will cancel, and I have this familiar theta double dot equal to minus G by L sine theta. Now here, normally what one will do is, immediately from here you will say that for small theta, sine theta equal to theta. So I will say this is actually theta double dot equal to minus G by L theta. So it's simple harmonic oscillator. Let me not make that approximation right now, and then proceed. Okay. Now this is my Lagrangian. Now I can, in order to construct the phase space, what I will do is, let me construct the generalized momentum, which I have written in the green box on the right side. P equal to del L. Sir, in this, okay, there is an anonymous attendee. It's very interesting. Sir, in a solar system, there is some certain orbit in which planets move. So the phase space of every planet has some different path. So can we say this is also quantized? They moving through certain quantized paths. Oh, I see. So the question is the following. The question is, since in harmonic oscillator, I said that the trajectory is quantized because of the Bohr's correspondence principle. The question being asked is, since I have different planets, the planets are moving in different orbits, then can this also be quantized? You see, but the point is the value of H cross is such that this, I mean, for solar system, it is almost a continuum. It is not, that's real space. Yeah, that is real space, yes. But then from that, no, there is somebody who answered. So Priyoda had answered saying this, that is real space in planetary motion. Indeed, that is true, but you can look at it this way. See, it's an elliptical motion. An elliptical motion, when you take a projection in the x and y, each of them is a simple harmonic oscillation. And so the phase space diagram of the x projection and the phase space diagram of the y projection, each of them is also an ellipse. Okay. Now, the problem is you can't, indeed it will be quantized, but that quantization will not lead to this, discrete orbits of planets which we see. That quantization is so small that you will almost see a continuum. Yes, exactly. So Harsh has written that there are asteroids moving anywhere anywhere they want. So not quantized. Yes, exactly. Because the point is, the quantization will be in extremely small steps. So on the scale of on a macroscopy scale, these are so small steps that it is almost a continuum. So this is not the thing which can explain this kind of a planetary motion. So that is the answer. Okay. Oh, no, that's okay. I mean, okay, so you're saying sorry, click this anonymous. That doesn't matter. Okay. So now, as I said, let us construct the generalized momentum. And the generalized momentum P is, I use the coordinate as theta. So generalized momentum P is del L by del theta, del theta dot. Now, now see, del theta dot, so if suppose I take the angle as a coordinate, then the corresponding generalized momentum is angular momentum. So what you see P here is actually the angular momentum. Okay, because that is a generalized momentum, just like linear momentum is the generalized momentum corresponding to the coordinate, which is Cartesian position. If my position coordinate is angle, then the corresponding generalized momentum is angular momentum. And so P here is the angular momentum. And it is very clear it is, because if I substitute it in the Lagrangian and take the differential, it becomes ml square theta dot, which is basically the moment of inertia I into omega, which is the angular momentum. Now, if I take this P and I substitute it in the Hamiltonian, I immediately get half P square by ml square plus mgl 1 minus cos theta as the Hamiltonian. And by the same mathematical machinery we have developed, we will calculate the Hamiltonian equations of motion, which is P dot equal to minus del H by del theta and theta dot equal to del H by del P. And then I divide these two as I did before. So I have P dot by theta dot is same as dP by d theta. And that is equal to, if I substitute, I'll get mgl sine theta by P by ml square. And now I can take this theta on the other side, the P portion on the other side, as before I can integrate it. And if I integrate it, the answer I will get is P square by 2ml square plus mgl into 1 minus cos theta equal to E. So this is my equation for the phase space trajectory of this particle, because this equation gives me a relationship between P and theta. Now let us go up. Now I'll tell you why this momentum phase space has a very interesting structure. Now go up, 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 up. I want to see the full figure. No, no, sorry. What I meant by up was, I mean, move the screen up so that I want to see something down. Further, further, further. I want to see the foot till the end of the screen. Yes. Okay. Fine. Okay. Sorry. थोड़ा सा नीचे हाँ ठीक है ठीक है. Now, so I see here the phase space equation. Okay. Now let us see how I construct these equations. Let us first consider the case of small oscillation. In a small oscillation, it means that the maximum variation of theta is going to be very less, much smaller than 1. When I say this, one should remember that here I'm talking of theta in radians. I mean, it is not that I have to take a fraction of a degree. I have to take the fraction of a radian. Okay. And so let us now focus on the figure which is having a light blue border, that is left bottommost. Now here I have taken the maximum value of theta as theta naught, so that theta is always between theta minus theta naught and plus theta naught, with theta naught much less than 1. Now I take this approximation and use this approximation in the phase space equation. So cos theta can be approximated as 1 minus theta square by 2. And once I do that, I can now substitute it there, and then 1 and minus 1 will cancel, and I will get the equation which I have written here if I keep only till theta square. That is P square by 2 ml square plus 1/2 ml square into G by L times theta square equal to E. Of course, there will be higher order terms because cos theta is an infinite series. But because of the approximation I have used, that theta naught is much less than 1, dp theta, just a minute. Can we just go up? I seem to have made a mistake. Somebody is... yes, indeed, that is true. Somebody is good that somebody has actually been alert and pointed out. The dp by d theta, which I have written, should have a minus sign here. That is absolutely correct. Okay. That should have... No, wait. No, it should not have a minus sign. I'll tell you why. Because, you see, there is a minus del h by del theta. Now, h has cos theta. Del cos theta by del theta is minus sign, and that compensates for this minus and gets a plus sign. That's why it is mgl sin theta by this. I hope it is clear. Who was it? Jahan. Is it clear? See, we are differentiating cos theta, that is already giving a minus sign, which compensates for the minus sign which is in front of cos theta. Okay, I hope it is clear. Okay, so yeah, let's go down. Yes. So now I was telling about the small oscillation where theta naught is much less than 1. So I said that when theta naught is much less than 1, and since theta is always less than theta naught, theta is much less than 1. So I can do an expansion of cos theta, which is 1 minus theta square by 2, plus there are higher order terms in theta. And I say because of the smallness of theta naught, the leading non-zero order is the theta square. All the other, so if I, that is what I mean is, if I neglect theta square, then there is only 0 left. So if I want to take the leading order term in which is non-zero, it is only theta square, and I write theta square, and I have got p square by 2 ml square plus half whatever theta square equal to e. Now if I plot this in p theta, this is the equation of an ellipse, exactly the same one which I did in the simple harmonic oscillator. And this is again shows that for small oscillation, the pendulum actually undergoes a simple harmonic oscillation. So I have shown it by the blue color, light blue color arrow. So this in that approximation is actually an ellipse. Now I take the absolute other limit that slightly go up. I want to see the green box also. Okay. Bus. So now, previously for small oscillation, what I did, I took the pendulum and slightly perturbed it so that it was oscillating. And now what I am doing is, I do the opposite. I give a huge momentum to the pendulum. Now what is happening? The pendulum will no more oscillate. It will keep going round and round in circles, the way I have shown. Okay? Because it has enough energy to go to the top and then come down also. So it will keep going round and round. And so now let us take it, bring it down. I want to see the phase space diagram. Yeah. Now for this green box, I have shown the arrow 1 minus cos theta, right? Differentiating it produces sine theta and a negative. Differentiating it produces. Okay, maybe you are right. Yeah, okay, just check it out. Yeah, okay. So, so Jahang is mentioning that, yeah, it's 1 minus cos theta. When I differentiate it, be plus sine theta, and though there'll be a minus sign. Okay, so that's yeah, you're right, Jahang. I think probably there is a minus sign missing there. Just check it out. Yeah, okay, yeah, that's correct. I think it's a minus sign missing there. Okay. Right. Okay. So now, so here what I was saying was, so the pendulum goes round and round. How do I look at this pendulum in the phase space diagram? Okay. First of all, what I see is that when the pendulum was oscillating, there were 2 points when the momentum became zero. Once the pendulum is going round and round in circles, momentum never becomes zero. So the phase space trajectory for that motion will never cut the theta axis, because on the theta axis, momentum is zero. And this is shown by the 2 red lines, which I have shown by the light green line pointing to the red line. When theta is zero, that is, it is at the bottommost point, then the potential energy is minimum and the kinetic energy is maximum. Since kinetic energy is maximum, the magnitude of the momentum is maximum, and that is why when theta is zero, the intercept on P is at the top, is at the maximum. So this is the maximum momentum. Now, as theta increases in the positive direction, the potential energy increases, the kinetic energy decreases, so the momentum decreases, and the red line comes down and the momentum decreases. When it is right on top, that is when theta is equal to pi, then there is enough energy that even after spending so much potential energy as going to the top, the pendulum is still not at rest. There is still some residual kinetic energy. So the momentum is still positive, but it is not as much as before. So it comes down to that narrow portion where it has a minimum. The momentum has a minimum, and that is the point where theta is pi. That is, it is vertically up. Once it has passed this point, now again the pendulum is coming down in height. The potential energy is decreasing, kinetic energy is increasing, so the momentum is increasing, and the momentum picks up and the red line goes. So this oscillatory behavior keeps going on. Okay? And similarly, I can draw the other one also for the momentum in the opposite direction. So I see that there are these 2 cases when the oscillations are for very small theta, and the other case where the oscillations are for very large theta. Now you have the case of a real oscillating pendulum, where the energy given to the pendulum is not so large that it can go around in circles. At the same time, it is not so small that it can be approximated as a small oscillation. And that is shown by the phase space diagram, which I have shown in green. And it is that purple or violet or whatever box which I have shown. So here, the theta is not necessarily small, but it does not have enough energy to go around in a circle. So what happens here again, so it is something like an ellipse, but it is no more the actual ellipse. It is a closed curve, which is a distorted figure. Okay. So Rajiv Das has asked to explain the red curve. Okay. So let us systematically go over it. Consider, unfortunately, I'm not able to use the whiteboard. Otherwise, I would have done something. Okay. So if the pendulum is straight down, then what is theta? Theta is 0. And the pendulum is at the minimum value of potential energy. So suppose I give the pendulum huge amount of energy. What will happen? The pendulum will keep going round in circles. Okay. When it reaches the bottommost point, which is theta equal to 0, it will have minimum potential energy and hence maximum kinetic energy and hence maximum value of the modulus of momentum. So I have momentum. I say let us look at the upper red curve. And so the momentum has a maximum value. As theta increases beyond 0, the height of the bob increases, potential energy increases, kinetic energy decreases, and hence the momentum decreases. That is why on that red curve, when I go on the right of the p-axis, the red curve starts going down. The momentum starts decreasing. Now, as the bob, the theta keeps increasing, the height keeps increasing till theta reaches the value of pi. Then the pendulum, I mean, I'm assuming that it is not a flexible string, okay? So it's not collapsing down. So this pendulum is now inverted. The bob is on top. Theta is pi. Now, this is the maximum height the pendulum can reach. And so this is the maximum potential energy that the pendulum can achieve. This in turn means that this is the minimum kinetic energy which the pendulum can achieve. And hence the momentum corresponding to this is the minimum modulus of momentum which it can get. And so if I see the red curve, it is coming to a point and there is a minimum in momentum. And so at this point, as we saw just now, the value of theta is pi. So at that point, the value of theta is pi and the momentum is minimum. When theta increases beyond that point, it can only come down on the other side. So again, the reverse happens now. The momentum, the bob of the pendulum is coming down. Hence, the potential energy is decreasing. Hence, the kinetic energy is increasing. And hence, the modulus of momentum is increasing. And so the red curve starts going up again. And again, once it has made one full round, again it will reach a maximum and again a minimum, and it will go on like a wave of water. Okay? Yeah. Now, if suppose I were to oscillate, if I were to oscillate the momentum in the opposite direction, then the theta is increasing in the negative direction and the lower red curve will be there. So it's exactly same as that. So the upper red curve is for clockwise motion. The lower red curve is for the anti-clockwise motion of the pendulum. But in both cases, the motion of the, in space, it will be clockwise. The point, okay, there is a question which is, so in phase space, the point right after theta equal to pi is a closed curve. No, it is not a closed curve because immediately after theta, it's a closed curve in the in real space for the pendulum. But in this phase space diagram, it will keep going up and down like a water wave. Okay, it will go. So here, so it is going from theta equal to minus infinity to plus infinity. Because, I mean, because, like, I mean, you can say that 2 pi plus theta is theta. But if I want to measure the number of rounds it has taken, then I keep on increasing 2 pi, 4 pi, 6 pi, and so on. And this wavy nature of the phase space diagram will continue for the red curve. Okay, I hope that is clear. Okay, whereas then, okay, now, so as I said, now I take the case of the green curve where the angle, what happens when the energy is dead and momentum of the bob stops. Okay. Okay, I will come to this. Okay, one question is, what happens, who is it? Rajiv Das has asked, what happens when the energy is dead and the momentum of the bob stops? I will come to this slightly later, and that is to do with the damped oscillator, the phase space motion of a damped oscillator. Okay, so now, okay, so now for a large amplitude oscillation, the green curve is there, and as I said, the bob does not have enough energy to go around in a circle, so it will not take the kind of phase space diagram which the red color curve took. At the same time, it is not small oscillation, so it won't even be a simple harmonic oscillator as the ellipse is there. However, it is a periodic motion, which means the phase space diagram will be a closed curve. And this closed curve will be not an ellipse, but a distorted ellipse kind of a thing. Okay? And so, if the green curve, I take it for smaller and smaller energy, gradually it will become an ellipse the way that blue color is. Okay? You can actually draw one borderline case here in which I have given just enough energy to the bob so that it goes to the top and stays. And okay, I have not shown that, so that will be in between all these. So this is the phase space structure of a real pendulum. Any questions? Just wait if there are any questions. Yes, okay. Time is a real physical quantity or for use as reference. Okay. So one question by Veerapandian Arumuham is time is a real physical quantity or used as a reference? Okay, it's a good question actually. You are asking a very philosophical question as to what is time. Well, time is a parameter. Okay, it is. I mean, it is a parameter with which we measure dynamics. Okay, as far as see, as I have given the example of the truck going through a desert. If a truck has gone through a desert, of course, time is a real parameter. But from the path of the path made by the truck, I cannot find out when the truck was there. Okay, so it is just that this diagram does not refer to time. That's all. Okay, otherwise there's nothing wrong with time as such. And Akshita Goyal has asked, does red curve suggest a circular motion since theta is only increasing in one direction, momentum is precisely, you have absolutely got it correct. It means it is a circular motion. The pendulum is undergoing a circular motion. That is why it keeps, see, if a particle is going round and round, theta is always increasing in a monotonically increasing fashion. Only when it oscillates, theta increases, decreases, and so on. So you are absolutely right, Akshita. It is actually indicates a circular motion of the pendulum about the point of suspension. Okay, so this is the structure of the real pendulum. Okay, so let us go to the next slide. Now I will come to the thing which people were asking yesterday. that, I mean, people were very disturbed, and understandably so, that the phase space diagram was discontinuous when I'm dropping a particle on a rigid floor. So now I will take a realistic thing, and instead of taking the, uh, I will keep the floor as rigid, but instead of a particle, I will take a ball, and the ball is deformable. That is, it is not rigid. So what I have taken is a ball of radius r. It free falls from a height h, and height h is the height of the center of the ball. And the free fall is as before in a constant uniform gravitational field. It bounces from a rigid floor. But now, since it is not a particle, but a three-dimensional extension, which is a ball, and I have made the ball as deformable. I mean, it doesn't matter whether it's the floor is rigid or the ball is floor is deformable or the ball is deformable. So I take a ball as deformable, and the collision is elastic. And now let us see what is the phase space diagram. Just come down a bit. Once again, I have taken the Lagrangian. Now here in the Lagrangian, y denotes the height of the center of the ball. Okay, just keep this in mind. And now what happens? The Lagrangian, as before, is half m y dot square minus mgy. The momentum is del L by del y dot, which is my dot. And the Hamiltonian is p square by 2m plus mgy. And since the energy is conserved, p square by 2m plus mgy is equal to energy. So now the phase space diagram as before, I have shown here, but there is a small modification. The equation which I have written here is only for the right-hand portion of the phase space diagram, which is a parabola. Why? That is because in this Lagrangian, I have only taken care of the forces involved where there is pure gravity. After the ball has struck the ground, in addition to gravity, there are elastic pressures. It is the elastic forces because of which there is this deformation of the parabola at the edge. That is near the p-axis. So now let me first go to the first one. So as before, I start from a height h. I forgot to write height h here. It is the rightmost intercept of the phase space path on the y-axis. I mean, it's a y-axis, but I have plotted y in the x-axis. Okay, y-axis is p here. So that is h. If you take the cursor and just go to that, then I can point out. Cursor. Yeah, so go to the right. Go to the right side on the diagram. On the diagram, no. Just take, this is the point h. This point. So this is the maximum value of the height. Once I drop it, as I told before, I mean, some of the arrow has gone somewhere. It goes in the negative p direction and goes along a parabola. But now how far it can go as a parabola? If the radius of the ball is r, the center of the ball can free fall only as long as the center of the ball is at a height more than the radius of the ball. The moment the center of the ball has come to a height h, the bottom portion of the ball has started touching the floor. Now, because of the existing energy of the ball and the fact that the ball is elastic, the ball can compress. Now, this is the difference. Yesterday, I was saying that it is not deformable, which means from this point where it goes, it jumps immediately to the top. Now, since the ball is deformable, the ball deforms a bit and the center can go slightly more than that height r. It can go closer to the floor, but clearly the center cannot go at the origin, because if it goes to the origin, then below the center, the ball is compressed to 0, which is not possible. So it compresses to a maximum limit, and so there is a deformation of that on the after that parabola is the deformation, and during this deformation the momentum now continuously changes from minus p max to plus p max. So the discontinuity is avoided by introducing deformability instead of making it a rigid ball. Priyanka, can you please repeat how the potential is mg 1 minus cos theta in the pendulum, is it? Okay. Oh, I didn't see it before. Okay, let me just complete this, then I will go back. Okay. So now the ball, the center of the ball, after the ball deforms and comes back to its original shape, the center again goes to the maximum, to the height of r. But by this time, the momentum has become reversed and we have got to the top of that phase space diagram, maximum momentum in the positive direction, and it starts retracing the path and starts going towards the height h. So this is the phase space diagram for a deformable, freely falling ball. Okay, are there any questions? I will. Okay. There are questions. Why is the information not received? Okay, Priyanka, I will just come to your question on that 1 minus cos theta right now after this, because it refers to the pendulum. Okay, Jahang has asked, why is it that the information of non-rigidity of the ball is not there in the equation? So that equation, you can. Okay, I mean, not that you can't, but it is more cumbersome because you have to write the equation in two ways. Okay, so look at it this way. Once the ball has deformed, what are the potential energies? Potential energy is one of gravitational potential energy, but because of the compression of the ball, there is an elastic potential energy. So the potential energy is complicated, and I have just approximated it by that smooth curve which I have joined. Okay, so you can actually write the potential energy, but it will be cumbersome because I have to include the elastic deformation. Before the tip of the ball touches the ground, there is no elastic deformation because there is no contact with the ground. Okay, so that is the reason. Jahang, I hope it is clear. If not, just let me. Okay, Akshita, does deformation suggest a finite time lag in momentum changing from minus p to plus p? Absolutely correct. Absolutely correct. The discontinuity would mean instantaneous change. The deformability implies there is a finite change. You're absolutely correct. Okay, then there is Arya Gori. What changes will come in the graph if it was inelastic? Good, very good. That is what I will come next, which is a dissipative system. Okay, so now I will just go back, backtrack and take Priyanka's question, in which in the moment, in the pendulum, she has asked me to repeat how the potential is mg 1 minus cos theta. Okay, just go down to the pendulum. Right. Or you can go, or you can take it down. I mean, I can explain by the other diagram, the lowermost diagram. Yes, yes. Now you look at this thing in light blue box. Now, I have this length L and a bob M. So, in this position, how much down is M? It is L cos theta distance from the top. If theta was 0, what will be the height from the top? It will be L. So by moving the bob from the equilibrium to this position, what has been the change in height? It is L minus L cos theta. So L into 1 minus cos theta. Priyanka, is it okay? Oh, this is Priyanka Srivastava. Okay.
Did you ask me? No, okay, Priya.
Okay, so probably it is okay. Okay. So this is the reason. I hope that is correct because I have not seen a response. Okay, fine. Okay, so let us carry on. Let's go to the next slide. Okay, so this I have finished. Okay, next slide. Now I come to the case of phase space trajectory with damping. And this was the question with Akshita, I think, asked, if it is inelastic, what happens? Now it is inelastic. Now let us start with the green curve. Now the green curve, which I have shown here, is the undamped thing of a ball falling down as I had just done. It goes as a parabola, then deforms, comes here and comes back to the parabola and goes round and round. Now, when it is inelastic, what happens? Till it touches the ground, it doesn't matter whether it's elastic or inelastic because it's not being deformed. So the path of the phase space will be exactly the same as the undamped or the previous case. That is, it will follow the green curve, okay, from the maximum till that negative p and then. However, when the center is at a distance r from the ground, the tip of the ball has now touched the ground. Since it has touched the ground, it has started deforming. But in the process of deforming, it is losing energy because of inelastic behavior. And so it does not have enough energy to compress the ball to the same extent to which it compressed earlier. So the center of the ball does not go all the way to very close to zero, but stays slightly away where the outer blue line is intersecting the brown axis. Once it is so, it now expands back. And so the center of the ball expands out. However, since it has lost some energy, the center cannot reach the same momentum as it did before. And the maximum momentum is slightly down. With this momentum, as if it is an undamped oscillator, it goes, but now because it has lesser energy, it reaches a smaller height, the blue line. Again, it falls down parallel to the previous parabola. Once again, when has come in contact with the ground, it deforms, but again, because of deformation, it loses energy and it cannot reach the previous point and it reaches below. And once again, when it is coming out, it has lost energy, so its maximum momentum has decreased even further. And so it has come to a height edge. Now this will keep continuing till the ball comes to rest. And when the ball comes to rest, after an infinite number of oscillations, what will be the center? The center will be on that brown horizontal axis at a distance r from the origin, and it will not move further. That is, it is at rest. Zero momentum and the center at a height h at a height r from the origin. So this is how the trajectory of the ball will move. Oh, sorry, it was not Akshita who asked, it's Arya Gauri who asked. I mean, Arya, is it, I mean, I will just come to Sarat's question. Arya, is it clear now what happens when the thing is inelastic? It is basically the thing will keep going inside as if it is a spiral. Okay, Arya has answered yes. Okay, fine. Arya Gauri, but the ending position is not clear. Okay, now Arya has asked that the ending position is not clear. So what I'm saying is, you know, after where I have left, it will go again and it keeps on going. But finally, so it will become a smaller and smaller and smaller figure till it reaches a point. And where will that point be? The point will be at a place where finally the ball will come at rest. And when the ball will come at rest, so there's a slight correction. The ball will come at rest. There is a small, so since the ball is not rigid, because of the weight of the ball, the center will not be at a height r from the origin, but slightly less. But it will sit there without motion. So the momentum will become zero and the position will be slightly less than r from the origin. Arya, is it clear now? Okay. Then there was one more question by Sarath. The direction will be always towards the converging point. Is it correct? Because why is it so? Because I mean, it is. I mean, it will be, because the point is the size of the figure is dependent on the energy. More the energy, bigger the figure. And since because of inelasticity, the energy can only decrease, the size of the figure can only decrease. So it cannot, so it will keep converging inside. Sarath, is it clear? Rajiv has a question. Okay, I will just come to that. The direction, yeah, I mean, okay. So anyway, so Sarath just asked me in case it is not clear. Okay, now Rajiv has a question. Now, what happens when the energy is dead and the movement of the bob stops? Oh, this was earlier. Okay. This too, sir. No, I didn't get it, Rajiv. So as I said, I mean, it just comes to rest. I just now said the ball comes to rest. So the momentum is zero, and the ball is lying on the floor. The ball has a finite weight. Because of the weight, the ball will be slightly deformed, and so the center of the ball will be at a height from the floor slightly less than the radius of the ball. That will be the point where it will come and rest. Okay, Sarah. Okay, Shweta. If momentum becomes zero, then finally the curve touches the q axis. Absolutely correct. Absolutely correct. So that is where its final resting ground will be. As I said, it will rest at a position such that the center of the ball is on the q axis at a distance slightly less than r from the origin. Okay, yeah, fine. So now, so this is for this one. Now one can ask the question, what about a damped harmonic oscillator? Okay, go to the next one. Yeah, it's here. It's okay. So here again, oh my God, I have given the same mistake here and put it as k by 2e. I just copy pasted that figure. Okay. So the blue line, blue curve is what we did yesterday about the undamped oscillator. And I don't know, I wish I could just correct it here. Okay. So instead of root of k by 2e, it will be 2e by k, I think. Yeah. Okay. So that is the undamped oscillator. Now, what is happening when the oscillator is damped? When the oscillator is damped, then the momentum, the magnitude of the momentum starts decreasing because of viscosity or whatever. So for that, for any position, the magnitude of the momentum is less than what it would have been when it is undamped. So starting from the extreme position, which is a green arrow, it will start moving, but it will start spiraling inside. So when it has reached the equilibrium position, that is q equal to 0, the modulus of momentum is not as much as it was before, but slightly less. And further, if it goes, because it has lost energy because of damping, the potential energy is now, the maximum potential energy is less. So it will reach a point on the q axis, not at the same point where blue curve intersects, but less. As it proceeds, it loses even more energy and the momentum becomes even less. And so like this, it will keep on spiraling inside till it reaches P equal to 0, Q equal to 0 ultimately. So this is how a damped harmonic oscillator behaves in phase space. Okay, any questions here? Momentum becomes 0. Okay, fine. Yeah, okay. So there is nothing. So now Can we go further down? Okay, so now so with this, I will now stop about phase space diagram. And the reason I emphasize phase space diagram was phase space diagram is an extremely important thing, and many problems you can solve without having to solve the equation of motion, but just looking at the phase space diagram. But unfortunately, in most situations, in most books and most courses, phase space diagram is not adequately emphasized. Exception being that when one is teaching nonlinear dynamics, it very heavily depends on phase space diagram. So we come to the next topic, which I call small oscillations. There was a ping sound, so I thought somebody has asked the question. Now, often when you have an arbitrary potential, exact dynamics is difficult to arrive at. A very simple example is a real pendulum. Unless you make an approximation that's a small oscillation, you really cannot get an exact solution to that. Because as I was mentioning, the number of problems for which exact solutions are available are very few in mechanics. But all is not lost. If suppose I have a general potential for a system, and it is such that the potential has a minimum, then what I can do is, I can ask a simplest question. I can ask the question that instead of talking about a general oscillation, I say that the particle is in the minimum. It is at rest, and I just perturb the particle. And so that is, I make small perturbation. Now the question is, how does the system respond in a general potential for this situation? Oh, somehow all those. It's funny, some things have gone. Okay, so just go up. Okay, no. Okay, so no, it's okay, So Vx is general potential. Now I had wanted to write x equal to x0. Okay, so I written x0. I don't know how it disappeared. Here also it disappeared. Okay, x equal to x0 be a minimum. So what do I do? So if x equal to x0 is a minimum, then dv by dx at x equal to x0 is 0. Now, what I can do is, about x equal to x0, I can make a Taylor series expansion of v of x. Here again should be v at x equal to x0. I can do a Taylor expansion. So v of x equal to, the first term is v at x0 plus dv by dx. I evaluate this at x equal to x0 into x minus x0 plus half d2v by dx square it should be. Oh yeah, when moving it, some zeros have gone somewhere else. That's why I see a 0 here. It should be, that 0 on top of that line should be actually subscript of v of x0. Okay, so I have d2v by dx square evaluated at x equal to x0. Again, I have forgotten to write x minus x0 whole square. I'm sorry. X minus x0 whole square, and higher order terms in delta x. Delta x is x minus x0. So this is my Taylor expansion, and now let us look at term by term what are they. The first term is the value of v at x0. So at value of v at any point is a constant value. Now I know that since equations of motion involve only gradient of the potential, a constant value of the potential, additive value of the potential, does not really matter to me. So a constant value of the potential will not affect my equations of motion. Now I come to the second term. In the second term, I have dv by dx at x equal to 0. But x equal to 0, I have constructed fundamentally by demanding that it is minimum. So dv by dx is 0 at x equal to 0. So the second term vanishes. So the non-zero term which can appear in this is the third term, which is half d2v by dx square evaluated at x equal to x naught into x minus x naught whole square, which I have forgotten. And so if I say that I consider small values of x minus x naught, so that I take only the smallest non-zero contribution, then I can neglect all the other terms which are written of the order of delta x whole cube. And so I can approximate this potential as, go down. Okay, bus. Yeah, so I've just explained here that if V of x naught is maximum, I mean minimum, not maximum. Okay, no, if V of x, the third term, yeah, third time I'm including, huh? Yeah, third term is d2v by dx square. I have forgotten to write dx square there. It should be dx square. Is that what the question is? I think it's Rajiv Das. Yeah, okay, fine. It should be d2v by dx square. Okay. Now here, suppose instead of minimum, x naught was a maximum. Then also dv by dx at x naught is 0. But the d2v by dx square at x naught will be less than 0. If it is a minimum, that thing will be greater than 0. Okay. And so as I said, the leading order Vx equal to constant plus this quantity. Here I've written x minus x naught whole square. Now, if that second derivative of V is greater than 0, then I can write it as V of x equal to a constant capital K plus half K delta x square, where K is d2V by dx square at x naught. And this is my familiar simple harmonic oscillator potential when K is positive. So what I see is, in general, when I have small perturbations, I can always approximate the potential as a simple harmonic oscillator potential, provided the second derivative of the potential at the equilibrium is a positive quantity. And that is why simple harmonic oscillator holds such an important place in classical mechanics. Okay, so I hope it is clear. Let's go to the next slide. Let me consider some simple example. I have a potential, say some arbitrary potential, alpha divided by x square plus beta into x square, with alpha and beta greater than 0. Let me look at the equilibrium position and consider the small oscillations around this equilibrium. I have dv by dx, if I take, it is minus 2 alpha by x cube plus 2 beta alpha. If I equate it to 0, then what will I get? I will get x power 4 is equal to alpha by beta. Here I should actually mention one thing, and it's not completely clear. Now, if x power 4 is alpha by beta, then technically x square should be plus minus square root of alpha by beta. But square root of alpha by beta is positive. Now x square has to be positive. So minus of square root of alpha by beta is not admissible. So I can only have plus square root of alpha by beta, because x is a real, because x square has to be a real, x is a real quantity. So x square is a positive quantity. Now x square equal to positive sine alpha by beta square root. I take a square root of this further because of x square. So x is plus minus 1/4 root of alpha by beta. Although x square cannot be negative, x can be negative. It can be positive or negative. So there are actually two solutions, x equal to plus minus alpha by beta to the power 1/4. Let us consider one of the solutions, which is a positive solution. Now I calculate d2v by dx square. And if I calculate that, that turns out to be 6 alpha by x power 4 plus 2 beta. Now if I take x equal to plus alpha by beta to the power 1 by 4, I get d2v by dx square at this point is 6 beta plus 2 beta, which is 8 beta. Can you just take it a bit more up? I mean, down. I mean, yeah, I want to see it. Okay. So 8 beta. But since we already said that beta is greater than 0, 8 beta is greater than 0. So Vx is a point of stable equilibrium. It is a minimum and not a maximum. Okay. So for small oscillations around this minimum, I can write V of x as alpha by x naught square, that is value of V at x naught square, plus beta x naught square, which is a constant. The first derivative term is 0 because of our construction. Okay, and this is what, so it is, that is what this is. This bracketed term at x equal to alpha by beta to the power 1 by 4 will be 0. So this term will go away. Further, I have got another term below. Who is handling the slide? Yeah, yeah. So that is then plus the second derivative term, which is half d2x by d2v by dx square at x equal to alpha by beta 1 to the power 1 by 4. X minus x naught to the power, oh, I'm sorry, this is the thing, since there's no whiteboard, I can't do online correction. It should be to the power 2, not 4. Okay, and so go down further. And so I have V of x equal to a constant plus half. Again, I have done a mistake. It should be 8 beta delta x square. I already cancelled it and put it. So it means that it should be 8 beta. So it means that the value of the spring constant k, effective value for this small oscillation, is 8 beta. It is half k delta x square. It should be 8 beta and not 4 beta. And the frequency of small oscillation will be omega equal to square root of k by m. So it will be square root of 8 beta by mass of the particle will be the frequency of small oscillation around this minute. Yeah, so that is what it is. I don't have any other slide further. I can discuss any doubts which are there, or Punita can tell me some list of topics which people wanted to discuss. Although X4 looks like it, sorry. Okay, very good question. So Harsh has asked that suppose you have the potential is x to the power 4. Even here, it is bound particle. And so the particle oscillates. So the question he has asked is, it can have simple harmonic oscillation, but it never has simple harmonic oscillation. Okay. It has oscillation, but not simple harmonic oscillation. The oscillation becomes simple harmonic only if the potential is quadratic. And so it does have simple harmonic oscillation. And this is an example, what you have given is an example of oscillation where there is no frequency in the sense of simple harmonic oscillation frequency. There is a time period of oscillation. There is a time period of oscillation, but it is not of the simple harmonic oscillation variety. I will take this example tomorrow. So the minimum point represents a circular orbit for a given potential. Why I'm talking about one-dimensional oscillation right now. It is a circular or an elliptical orbit in phase space, if that is what you mean, Samarin. Oh, yeah. Any other question? I think people have got tired. Uh, uh, Punita, are you there? I mean, I can see a big D written there. So, I mean, she was saying that there is a list of questions, which topics which students wanted me to cover. So, I just wanted to have a list. Yeah. Okay, so there are no other questions. I don't have anything else today because, again, this is a, yeah, unfortunately, I cannot do an online whiteboard, so I can't do anything further. Tomorrow, I will continue with some examples of non-harmonic oscillation. Okay.
Yeah, that is all right, sir. So it was
Now,
a really informative session.
hey, Bapriya, sure.
So I think anything else if you want to say to the students?
No, nothing. I just wanted that. You were saying some topics which they wanted to know. Have they given the topics?
I don't know actually about the topics. Punita ma'am can only tell.
Oh, it's somebody else sitting on Punita
Yeah,
Man's. Okay,
yeah,
Mansi.
yeah,
Hi.
yeah. Mansi
Okay.
here. Yeah.
Okay.
Hello, hello, sir.
Hi. Yeah, you did not hide yourself. Okay. Yeah, okay. So, yeah. So, I mean, okay. So, I don't have anything else to say. I mean, if there are questions, I can answer. There is a chat box. There is something. So, topics are being collected. Okay. Okay, then I'll see you tomorrow. Just a minute. There is one more question. Session. Oh my God, it's a. Understand human condition. My God. Oh, it's a. Okay. Okay. Hmm. Yes. Okay. Okay. See you then. Thanks a lot. Bye.
See you, sir. Okay, thank you.
See you. Bye. Bye.
Bye. Bye. So with this, we come to the end of today's webinar and um the tomorrow timetable here I'm showing right now. Yeah. So this is the tomorrow subject that we are going to discuss. So tomorrow we'll have first a talk from Professor Gautam Gangopadhyay, Department of Physics, University of Calcutta, and after that we'll have a talk from Dr. Professor Samit Mandal, Nuclear Physics, Department of Physics and Astrophysics, University of Delhi.
Yeah. Dr. Mansi, Dr. Parul,
Yes,
Yes, ma'am.
you've ended everything?
Yes, ma'am.
Okay, good.
Sir has left, so he asked to wind up. So we wind
Yes,
up.
yes,
Yeah.
it's perfectly okay. Every day we don't
Yeah.
have to really stretch till 8:50. Okay, so that's fine now. Thank you so much for all this, right? And because I'm the host, so I will now end the meeting, right?
End the meeting and ma'am, stop on live streaming